talk of today. We have David Dumas, who's going to talk about the Python visualization for the mathematical world. And I made up your title.
Okay, thank you. So, I'm David Dumas, and I'm a mathematician from the University of Illinois in Chicago. And my research is in hyperbolic geometry, complex analysis. It doesn't directly use computation. It's not directly connected to the theory of computation. But whenever I can, I like to incorporate mathematical visualizations or computer experiments into my work. And so what I'd like to do today is to pick one of those as an example and to describe a mathematical visualization project related to hyperbolic geometry that uses Python. And along the way, by describing that project, both the mathematical aspects and how they map to code, to highlight characteristics of Python that make it suitable for this application. So what I'm going to tell you about today is a visualization project that makes a picture of an object, a mathematical object. The name of that object is the space of projective measured laminations, which often goes by this abbreviation PML. It won't be so important what that object is. I'm going to go through the details of what the visualization shows. But I should say that everything that I'm telling you about today is a joint project with Francois Guéréteau, a mathematician at the University of Lille. And the URL that's given at the bottom of the slide there is a place where you can find more information about this visualization, related ones of the same sort, link to a GitHub repo that has all the demo code from my talk today, as well as full demonstration of the kind of rendering that I'm showing you. And that URL is on all the subsequent slides, so don't worry about jotting it down right now. So let me tell you, the 3 steps that the rest of the talk is going to cover are basically the steps that would be involved in making a scatter plot in 2 or 3 dimensions. You have to have some data set that you want to show, so you have to enumerate the objects. You need to choose which characteristics of the object should map to coordinates. So you have to choose your coordinates properly. And then finally, you have to render an image. And I'm going to say something about each aspect here and how it plays out in the specific problem under consideration. So let me tell you what our problem is, because the objects are not going to be rows in a data set that comes from the real world. Instead, they're going to be topological objects. And this all fits into what you could call a topological enumeration framework. So let me give a simpler example of a topological enumeration problem that you may have encountered in your everyday life. Suppose you're trying to walk from one place to another, marked here as start and finish, but there's some kind of obstacle in your way. Maybe it's a hole that you don't want to fall into or a telephone pole that you don't want to walk into. I think you know what I mean when I say that you have essentially 2 ways to deal with this problem, and they are to go around the obstacle to the left or to go around it to the right. Now, I do not mean that those are literally the only 2 walking paths that you could possibly take, that those 2 pictures are the only paths. I mean, of course, you could modify the path that goes to the left just a little bit. And I would say that that makes the same essential choice in this problem. More formally, what I would say is you cannot turn the blue path into the red one by moving it around without crossing the obstacle. However, you can turn these 2 blue paths into one another by making small changes and never crossing the obstacle. So that's the kind of equivalence that's going to be in play for the rest of the talk. You're always allowed to move things around, but never across obstacles. Now, you might object and say, I can imagine at least one other way to solve this problem. I could do a kind of 360 around the telephone pole and then go to the finish. So let me use that as an opportunity to introduce an arbitrary rule that's going to be in play for the rest of the talk, which is that this is not allowed. We will not allow any paths that have self-intersections, and in mathematics, the convention is a path is called simple if it doesn't cross itself. So no simple paths from now on, get rid of that, and we've solved our topological enumeration problem. This one does not produce a very interesting scatter plot. The space of simple paths that avoid this obstacle and go from start to finish is a 2-point space, and so that's a picture of it. The more interesting problem I'm going to tell you about is one of enumerating paths, in fact loops, on a different surface, not the surface of the Earth, not a plane, but on a 5-holed sphere. So imagine here that this is the surface of a sphere. It could be a ping pong ball or a beach ball or something, and that you've put 5 holes into it. These holes are going to play the role of the obstacle. Because the holes are missing, you can't actually go through them. You have to go around them somehow. And we're going to be talking about enumerating loops rather than paths because the start and end are going to be the same. and not approximately the same, but literally the same. All the curves that I draw from now on will have to be closed. They start and end at exactly the same place. This is significant because of that simplicity assumption, the requirement that the paths don't have any self-intersections, because some perfectly reasonable looking paths that go around the obstacles and come back very close to where they started cannot be exactly closed up without introducing a self-intersection. This figure 8 path is an example of that. If you try to close it up, you will necessarily cross yourself, and so this is deemed illegal and thrown away. Okay, so having most of the arbitrary rules out of the way, I should also say that I'm going to draw the picture a little bit differently from now on, mostly because all of the pictures I had before were drawn in this other convention. I'm going to draw the same surface like this, where I've taken the 5 holes and I've pulled them outward to be the punctures just at 5 points. So a sphere, which before was nice and round, has now become a kind of pentagonal pillow. It has a front, it has a back, and it has 5 holes or punctures that have become these very small points. And the curve that I had drawn before that goes around two of those punctures now becomes a curve that has half on the front, half on the back. I'm also going to get rid of the pretty pink background, and just for simplicity. And something you may have noticed about this curve that is going to play a role in the rest, and is the last arbitrary rule that I'll introduce, is that this curve has 2 sides to it, which I've colored green and yellow in this case. And you'll notice that there are 2 of the punctures on one side and 3 on the other. You could call this a kind of 2-3 closed loop on the 5-hole sphere, and those are the only kind we're going to consider from now on. All the others, uninteresting, get rid of them. I mean, the truth is, you could do this for any of the other types. The 2-3 case is the one that leads to the most interesting mathematics, and so it's the one I'm going to concentrate on. So bearing with me on that, I should tell you that these curves have a name. They're called the non-peripheral simple closed curves on the 5-hole sphere, and I might abbreviate that to NSCC from now on. Okay, so that's what we're enumerating. You can see that there are some of these. I have one example that I've been working with on several of the slides so far. I'll bet you can imagine at least 4 others just looking at the picture, right? I mean, you could take that one and rotate it around and get these. Maybe I'll call these the basic curves, the 5 most basic examples you could produce of these 2-3 or non-peripheral simple closed curves. But let me just quickly convince you that there are others. You could take those last 2 that I showed you and do a little bit of cut and paste to produce a new simple closed curve. That's an example. And that's not on our list so far. Here's a more complicated example that I'll give some more details on later, but this hints at the kind of thing that could allow you to produce a whole lot of these things. You see how this example winds around a lot, and that will allow you to introduce more and more complexity without crossing yourself. Okay, so that's our topological enumeration problem. How are we going to turn this into a coding problem? We need some way of encoding a curve, which is a sort of continuous object, into a data structure. So for that, we're going to use strings of characters that represent curves according to their component parts. So let's introduce names for some basic operations that you can do. A will mean you're in the starting area, you go around one of the holes, and you come back to where you started. B will mean that you do the same thing for one of the other holes, C, D, and E. So these 5 basic pieces of a path have names that are lowercase letters, and they all mean going around the hole in a clockwise fashion. If you do the same thing in a counterclockwise fashion, we'll use a capital letter. So in this way, a sequence of characters can represent a sequence of things that you do in order, and therefore encode a curve. And I'll just keep the names for the 5 punctures there for reference, but if you consider the string AB, that represents first do A and then do B. So you go around hole A and then hole B, and you get a curve. But remembering our rule that you're allowed to make small modifications to the curves, you're just not allowed to drag them over the puncture, this is actually a curve that we've seen before. We just push it a little bit, we're down to one of those 5 basic curves I showed you before. So the string AB represents that one. BC represents this other curve, another one of the 5 basic ones that goes around 2 of the punctures. AC is another example of a simple curve. And this is a good time to note that all the curves I've drawn so far are oriented. You could go around, they specify a direction in which you should travel. If you reverse the orientation of the curve, that is equivalent to reversing the string, but also switching lowercase and uppercase. So CA would represent the same curve with the opposite orientation. This is also a good time to observe that not all strings work. If you consider the string lowercase a, capital C, that represents one of these figure 8 curves that has this essential self-intersection, and I get to bring out the big red X again. Okay, so that example that I had shown before as the more complicated one can be represented as a string of length 5. And to see that this is a proper encoding of that curve is a little bit complicated. You have to do quite a bit of this moving around. But it's a general fact that any curve, any closed curve on this 5-punctured sphere can be represented by a string in these 5 characters A through E and their associated capital letters. How would you go about generating a list of these things? Well, let's consider the simpler problem of generating just all of the words in a fixed alphabet of letters A, B, C, D, E, and their capital letters. If we restricted to just a fixed length of word, like 5 in this case, then the product operator from the itertools module provides a nice way to sample, with replacement, a fixed number of elements from any iterable. So we can use the string A, B, C, D, E, A, B, C, D, E here, and then W in this loop will just contain all possible 5 tuples taken from that string. And so this loop, if you were to run it, would just print out all of the possible 5-character strings made from that alphabet. Now, I've, of course, skipped a step here, right? I should really check if they're legal, if they represent curves that don't have self-intersections. And I should probably, at the same time, make a note for myself that I ought to implement the check. And I won't do that, because what I'll explain next is that this is not an ideal approach to the problem, and something better is needed to get good results. So what's the problem? The problem is that is simple will basically always return false. You're searching for a tiny needle in an exponentially growing haystack. So here's an example. If you look at all of the words of length 2 in that alphabet, and you highlight in red the ones that represent simple curves, you get a picture that looks like this. Pretty good, right? We have a good number of them. If you go to words of length 3, I don't know if maybe it's a little bit hard to see the red there, but there's quite a bit less of it. Let's jump all the way to words of length 5, and let's represent each word with a pixel. Then here, the gray pixels are curves with self-intersections, and those few scattered red pixels are the simple ones. So we're searching for a very small needle. It's in general true that the number of words of a given length grows exponentially in length, whereas the number of those words that represent simple curves grows only as some power of the length. So asymptotically, they represent 0 fraction of the words. So here's another approach that you could use to the same problem, which is never introduce any curves that have self-intersections at all. Start with some curves that you know to be simple and modify them in a way that preserves the property of being simple, preserves not having any self-intersections. So twisting is a way to do that. I'll explain the twisting operation now. This is an operation that has a kind of input, a target curve, BC in this example, the blue curve, and also some information about where you're going to modify it, which is the twisting curve, or CD in this example. It's shown in red. So the first thing that you do is you thicken the twisting curve to a ring, and now we're going to change the target curve wherever it crosses through the ring. We're going to delete all of the places where it traverses the ring, and instead of having the curve cross straight across, we're going to introduce a 180-degree turn as it goes through the ring and reconnect the strands. So after doing this, the curve that was the target curve has become the curve that we would encode by BD. And this is a general operation that you can apply to any simple closed curve and produce another simple closed curve. In naming the operation, I would call this the twist around CD, or TCD. You can do this several times if you want and introduce more and more twisting in that ring. The nice thing is that this operation that I just described is actually equivalent to a string operation. Doing this changes which curve you have, and it does so in a predictable way. All you need to know is the string representing the curve, and you need to replace each C that appears with D, and separately, each D that appears in the original curve you replace with capital D, CD. It's in fact true that each twist in one of those 5 basic curves, AB, BC, CD, DE, and EA, the 5 simplest curves that I showed you before, can be represented by a simple rule for how you replace each of the 5 characters A, B, C, and D with other strings. And the contents of this table are not so important. What I want to highlight is the fact that this table exists. All of these twisting operations, which take simple curves and give you new simple curves, are represented as tables of replacements for the 5 characters. Now, what's the topological fact that makes this work? It's that these operations suffice to turn any simple curve on the 5-fold sphere into any other. It's true that these twists in the 5 basic curves and their inverses, applying those in some sequence can turn any simple closed curve on the 5-fold sphere into any other. For that reason, because of that, there is a natural algorithm you could use to produce a big list of simple curves. You simply start with some curves that you know to be simple to begin with, call those the seed curves, and then you apply a bunch of twists, say all of the twists in those basic curves. Then you get some new stuff, call the new stuff the frontier. Then you apply twists to everything in the frontier to get some more new stuff. The frontier evolves, you keep going until you decide that you're done, or you run out of memory or disk space or the free tier on Amazon Web Services or whatever. And then you say that's our list of curves. Okay, what I just told you was a lie because the twists don't always give you new things. Sometimes you're undoing a twist that you had just done at the previous step. So the picture's a little more complicated. Applying twists will give you a mixture of duplication, things you've already seen, and some new stuff. But as long as you only remember the new stuff and apply the twist to those, the same basic algorithm applies. You apply all the twists to all the things on the frontier, you filter out what's genuinely new, and then you do the same thing again. You get some big list of curves. So let's see what that new algorithm, the twist-based generator, would look like in Python code. So let's assume here that you already have these functions, TAB, TBC, and so on, that perform those replacements on a string. The Python set data type is perfect for this kind of thing. It's meant for storing collections of distinct elements, so it takes care of filtering duplicates out for you. And it supports efficient Boolean operations. So in this case, what we can do is have a collection of curves that's initially the empty set, have a frontier, which is everything that is brand new at this step, which is initialized to just contain our seed curves, and then we do the following 3 lines of Python, however many times is the depth we want in this kind of tree of possible twisting operations. So what you do is, here using a Python set comprehension, you apply every twist, t, to every curve x in the frontier, and take a set of all of those. So this filters some duplicates. We call that latest. Then we need to calculate the frontier, which is all the latest curves, but removing any that we have seen before. So this is taking the difference of the 2 sets, which is supported by Python set data type. And then finally, you should make a note of the fact that now the frontier has been seen and add it to your big bag of curves with this update call. Update could be called take union with. After this call, curves is equal to the union of the old curves and frontier. So this is the generator. Now we have some gigantic collection of simple curves on the 5-fold sphere represented by words, and we have to decide where to put them, how to make a good picture. So this was actually the inspiration for the project, was that in 1986, the mathematician William Thurston described a way to associate 4-dimensional vectors to curves on the 5-fold sphere. In fact, he described a way to associate a vector in some space to a curve on any surface, and we're just doing what is the simplest case, the case where it's only 4 dimensions, and so there's some chance of visualizing it. So I will tell you in a moment how this calculation of a 4-dimensional vector works, but what you should know right now is that the resulting cloud of points in 4-dimensional space doesn't go everywhere. They end up clustering around a surface in 3-dimensional space, in 4-dimensional space. It's a hypersurface, and so it's a 3-dimensional object sitting inside of 4 space, and that object that these curves cluster along, that they densely fill, that's the thing that is called PML, or projective measured lamination space. But we'll just be talking about the cloud of points from now on. All right, so now I have to do, this is the only point at which I think I really have to take a rabbit out of a hat. I can't tell you all about hyperbolic geometry, though I would love to. But I'll tell you, functionally speaking, what hyperbolic geometry gives you in this whole procedure. So it turns out that you can take the 5-fold sphere and associate to it a beautiful tiling picture, a tiling by pentagons, not of the plane, not of the Euclidean plane that we're familiar with, but of the hyperbolic plane. And this is a picture of one of those objects. It looks kind of like an MC Escher print, if you've ever seen one of those, like circle limit, 1 through 4. And here's what you can do. Using one of these tilings and any curve x on the 5-fold sphere, you can get, by some magic, a 2x2 matrix. I'll call it rho of x here. And then by looking at the numbers that appear in that matrix, you can calculate a length for the curve. That length is a hyperbolic length, not a Euclidean length, but it doesn't matter. It's just some number. So let me just quickly sketch what the calculation would look like. It turns out that the tiling directly gives you the 2x2 matrices that you should associate to the generators, A, B, C, D, and D. And then, if you want to calculate the matrix you should associate to some other word, like A, B, C, B, what you do is you take the product of the matrices corresponding to those individual letters. And then you get some matrix out of it. To calculate the length, you then substitute the sum of the diagonal entries of the matrix into some trig function, which doesn't matter, and you get a number out of it. So this is a machine for taking a curve and a tiling and getting a number. Thurston's great idea was there isn't just one tiling of the hyperbolic plane you can use, there are many. So let's consider what happens when you make an adjustment to the tiling. So you move the tiling a little bit. Then everything in the picture changes. There's a change to each of the matrices, and there's a change to the length. So now we get not just a length associated to x, but also a change in length associated to this way of modifying the tiling. Why four-dimensional space appears in this whole problem is that there are 4 essentially different ways of modifying the tiling. So if you repeat this same procedure for 4 different ways of adjusting the tiling, you get 4 delta length quantities associated to x. So assemble those into a vector with 4 components, and that's what you could call dlength, the differential of length. It tells you how length changes as you adjust the tiling. So how would a calculation of this look in Python? Maybe I won't go into a lot of detail about the method that's displayed here, which is a factory function. But let me just say that the core is you do it using NumPy's matrix algebra, which is very nice. And we use a recursive method. You take a given word x that you're trying to compute the matrix for, and you split it into 2 parts, the first part and the last part, that each has roughly half of the letters. You calculate the matrix associated to each of those halves by making a recursive call to this function rho, and then you take the matrix product of those 2. So this recursively splits a long word into smaller pieces until you get down to a base case, in which case you just use the matrix associated to that generator according to your tiling. So this kind of recursive call is quite efficient. And the other base case I should have mentioned is if you start with the empty string, you should return the identity matrix. Okay, maybe I'll summarize this next part just by saying that once you can calculate the length associated with a curve, you can calculate the differential of length associated with a change in tiling just by taking differences. Okay, so what do you get out of this? You get a big list of 4-dimensional vectors associated with all of those simple closed curves. The next problem you encounter, though, is that 4-dimensional space is relatively difficult to visualize. Or it is for me. I don't know about. Talk to me afterward if you are uniquely skilled in seeing 4-dimensional spaces. So we use a dimensional reduction technique to address this, where we take this kind of hypersurface in 4-dimensional space. Here it's shown as a square that has a cloud of points sitting around it. We inflate it to be a sphere, and then we open up the sphere and we flatten it out onto 3-dimensional space. The specific way that we do it is not so important. You're probably familiar with things like the Mercator projection that take the Earth's surface and spread them out onto a 2-dimensional plane, even though the Earth sits in a 3-dimensional space. We do something similar called Stereographic projection that opens up the sphere and flattens it out onto a 3-dimensional hyperplane inside of R4. The formula for it is at the bottom, but just think of it as a dimensional reduction step that introduces distortion but lets you see a 4-dimensional data set with just 3 variables. So after you do all this, what do you have? What you would have is a big list of maybe 1 million or 2 million rows that tell you a word representing a simple closed curve. Maybe you might want to keep the length of that curve around. And then these 3 variables, x, y, and z, that represent the projected version of the sensitivity of that length to different changes in the tiling. Here's an idea. Rather than just rendering points to display this, it might be a good idea to make the short curves more prominent simply because they are fewer in number and they represent, allow you to see important features of the set of curves in your picture more readily if you highlight the short curves. So what we decided to do was to illustrate a curve using not a dot but a sphere, and the radius of the sphere is inversely proportional to its length, considered as a curve. So the question then is, what is your best choice for, and I wish I had gone to the previous lecture when we were considering this question, what is a good way to use Python, if possible, to make a picture of millions of spheres? And our particular constraints in this problem were that real-time rendering is not essential to us, but having an accurate picture that includes all of these millions of data points is. So we decided to party like it's 1992, not with a refreshing Crystal Pepsi, but with ray tracing. So the technique we use to make this picture is to use the open source ray tracer POV-Ray, which includes, as one of its geometric primitives, a sphere of a given radius centered at a point. You don't have to deal with meshing, triangles, anything like that. You can just say sphere at this point with this radius. The great thing about Python for this part of the project is that Python is great at talking to other languages, other programs, especially if it speaks any kind of text. So in this case, we simply take our data set and we write out a list of sphere primitives using the 3 coordinates computed from the differential of length calculation, and 1 over the length of the curve used, it turns into the radius of the sphere. If you take this and you append a little bit of boilerplate code at the beginning and the end to set up things like lighting and the camera, then you get a full scene file that you can then feed into POV-Ray and make some pictures with. So now I'll just show you some of those pictures. The first one is just going to show you all the simple curves on the, or a large number of simple closed curves on the 5-punctured sphere shown in R3, and it's going to rotate in 3-dimensional space so that you can see it from different sides. This was produced by rendering individual frames and then later assembling them into a video file using FFmpeg. So this was really satisfying. I have a feeling that when the first time I got to look at this picture, I feel the way astronomers must feel when they see these cosmic background radiation anisotropy plots, where you see, I've always imagined how that must work, but it's really satisfying to see it. And you see that it has this intricate structure. What you're looking at is somehow an intrinsic structure that exists in that 5-fold sphere in its topology, reflected in this 3-dimensional data set, this cloud of points. And you might notice it has this kind of self-similar structure. Little pieces of the picture end up looking much like the whole picture. That is basically because all these operations like twisting, you can do them not just around the 5 basic curves, but around any curve. And that forces the picture to essentially look the same around every point as it does in the large scale. I think I'll interrupt the rotation to show you another view of this. That rotation was happening inside of 3-dimensional space. But remember, the original object was in 4-dimensional space. So it makes sense to also take a 4-dimensional rotation of the object and then project that out to 3 space. So what you're about to see now is an image of the same data set, but rotating in a way that is not compatible with the stereographic projection. So things appear to bend and distort in this 3-dimensional projection. To a 4-dimensional person, this would just look like rotating around the z-axis. So while this animation is playing, I don't want to interrupt your enjoyment of it, but maybe I'll point out some features of the picture. Do you notice that there are these 5 really big spheres here that are arranged in a pentagon? So can you imagine so those have to represent 5 non-peripheral simple closed curves that are arranged in some way, 5 non-peripheral simple closed curves that, because these spheres are very large, they must be very short curves. So what could they possibly be? Those are just the 5 basic curves that I talked about from the beginning, A, B, B, C, C, D, and so on. Okay, and similarly, you could identify these second shortest ones that appear kind of to be coming toward you, and those are the curves A, C, B, D, and so on, that use 2 letters but not necessarily adjacent ones. So maybe I'll show just one more view of this. This is combining rotations in 3-dimensional space and 4-dimensional space. The point of looking at these different kinds of distortion operations is to get a feeling for what the four-dimensional data set looks like, you need to be able to look at something like this and say, sure, the shape of it is not changing. I'm just changing my viewpoint of this single four-dimensional object. So here you can see that the 5 basic curves go from being an irregular pentagon to being all along a straight line. Okay, so I think I'm just about out of time, so I'll stop there.
You can ask to him wherever you want to ask him outside.
Sure, I'm happy to talk afterward.
Thank you very much.